Okay, and I think I probably said it might be helpful to create like a display method or something like that. All right, so let's start with that first part. Let's go ahead and fill an array up with some random integers and then sort that array. Let me make sure it's recording. Okay. So let's go ahead and we'll do all of this inside of our driver class here for our first step. I think I probably said it didn't matter whether you did it all in driver or wanted to go outside of that. Right now we're kind of drilling arrays, then we'll start piecing them out into some other things. So if you're going to create a collection of integers, we're going to need an integer array. So it's always going to start off this way. Int array is the type. Name it whatever you want. Equals new, then how many you're going to store. So let's say we store, well, let's, for the sake of sorting, let's start with 5, just so we can see it. Okay? So we're going to start with 5 integers. Now, some things that people were having issues with when they were messaging me on Slack was things like, oh, well, I'm going to print out AR. Well, what's this going to give me if I print out AR? It's going to give me a memory address, and we talked about that, why it's going to give me a memory address. That's this dude here. The variable AR actually holds a pointer to where the array actually lives in memory. That's why I get the memory address from there. Okay? So that'll give me a memory address. What I need to do is I need to spin through every element of that array. How many elements are in AR? AR.length. Okay, so AR.length number of things, which in this particular case happens to be 5. And we need to go ahead and we need to fill AR up with some random numbers. Okay. Now, how do we generate random numbers in Java that we using the tools that are in our tool set? Every single one of you should have just done this homework assignment where you generated random numbers. How did you do that? Random class. All right, so I'm going to need the random class to help me generate some random numbers. Once you create the random class there, it's going to yell at you and said you need to import java.util to give you access to it. I just need to click it better. Still need to click it better. Nailed it. All right, so now we have the random class there, and we can fill it up with random integers. I don't care if you do complete random integers between -2 billion and +2 billion, or if you want to keep it between 1 and 10, whatever makes you happy. Okay, the drill for this assignment was not, how great your random numbers are. The drill for this assignment is work with arrays, fill it with some random numbers, and then let's come up with our own way of possibly putting those numbers in order in a pretty ghetto way. Okay, and we're probably going to be looking at some better ways of doing that. It's kind of where we're going with this. Okay, so let's go ahead. So how do we, now that we have the random object, how do we use that object to generate for us a random integer? NextInt method. All right, so we say r.nextInt, and let's go ahead and just give this guy a value 10. That'll give us a number between 0 and 9. All right, so we'll just generate a bunch of numbers between 0 and 9. All right, so if I run this program right now, what will the output be? Nothing. Why? I'm generating, in this case, 5 random numbers between 0 and 9. I'm literally doing nothing with it. I'm not displaying it. I'm not putting them in my array. I'm not doing anything with it. Now, I said I want you to create an array capable of holding some integers and fill that array up with random integers. So here I have a place to put integers. Here I have a way of generating integers. So let's go ahead and put those integers in a place. So we're going to stick whatever random numbers generated by saying r.nextInt into bucket I of AR. Make sense? All right, what would the output of this program be? Still nothing. I've done some work though this time, right? I've generated some random numbers. I've thrown them into my array. I put a random number at bucket 0. I put a random number at bucket 1, a random number at bucket 2, a random number at bucket I, each time through. Okay? So when this loop is done, AR is filled with random numbers between 0 and 9 in this case. All right, so if I do system.out.println and I print out AR, what am I going to get? AR.length is the length of AR. If I just print out AR, what am I going to get? Memory address. Okay, not my random numbers yet, right? I get the memory address of AR. It's telling me AR holds a memory address. It's telling me where in memory my random numbers are currently stored. So now I need to go through and show those random numbers, proving to myself that I got random numbers in that array. So let's go ahead and write a function that will display the contents of an integer array. All right, so we'll make this guy static since we're going to be calling it from a static context. That is, we're calling it from within this class, and it's going to be owned by the class. And we're calling it from within main. And since main is a static method, we can say that we are operating inside a static context inside of main, because main is static. Okay? So we'll go ahead and create a second function here outside of main called, let's make this guy void. Let's call it display, and he'll take an integer array as a parameter. All right, and just so we don't get confused, let's call this guy elephant, just so we're not connecting this AR with that AR. I would probably still call it AR here, but let's just, for the sake of our example, make sure we use very different variable names so we understand that we're going to be passing this array into this local variable and using it in here. All right, so I want to create a loop that's going to go through every element of elephant and display it to the screen. All right, so here's our go-to loop for int I equals 0. I is less than, how many elements are in elephant? Elephant.length number of elephants. Probably a bad choice of variable name. Elephant.length number of elements. I++. And each time through, I want to display a number, whatever value stored at the current position, that is position I inside of elephant. So I'll do a system.out.println elephant at bucket I. Okay. What would the output of my program be now? Still a memory address. All programs begin and end with main. What does main say to do? It says generate an integer array, generate an instance of the random class, go through that integer array and fill it up with some random integers, then print out the memory address of that array. That's all my program currently says to do. I have this extra method down here that could do something if I were to call it. All right, is this a class method or an instance method? Class method, how do you know? Perfect, so we're looking at the method definition here. It's a class method. We know it's a class method because it says static at the beginning of it. How do we call class methods? So you told me how we can identify a method as being a class method at the time of definition by seeing the static keyword there. So now that we know this guy's a class method, how do we call him? Using the name of the class in which the method was defined. So this method was defined inside of a class called driver, so we would say driver.display. So I'll go ahead and say driver.display, and he wants me to pass him an integer array. I have an integer array here called AR. All right, an AR is an integer array that happens to have 5 elements, well, happens to have a place to store 5 elements. We've filled it up with 5 random integers. We've passed it into our function down here, display. So elephant will be equal to the same value as AR is equal to. So if we kind of draw that picture here, I get this kind of animal. Elephant and AR both point to the same place in memory. They both hold the same value, which is the memory address where this single array lives. All right, so this would be an example of passing by address, not passing by value. All right, we have sent the address of AR. Well, we've sent in a memory address, which is the address that AR holds, into our function, into our method, and stored it inside of a variable called elephant. So now elephant and AR are both pointers. They're pointers because they hold memory addresses which point to a place in memory where, in this case, that array actually lives. Make sense? Okay, so now what does main say to do? It says to do all this crap we already talked about. Then it says print out a memory address. Then it finally says call the display method. The display method takes in an integer array, goes through every element of that integer array, and displays it to the screen. So what will the output of my program be now? Okay, so it'll be a memory address right there, right? Because we're still printing that, followed by, in this particular case, 5 random integers, because that's what the display method does. All right, so there's my 5 random integers. Memory address followed by 5 random integers. We want to dump that memory address right now. Let's just get our 5 integers, so we're working with that stuff. Okay, so 55915, 76082. So certainly we're seeing that these are random enough for us at this point. You know, we could argue something you talk about a couple different places. You talk about it probably in the security class with Professor Wall, then probably also in Senior Seminar 1 with one of the Locklairs. Either Dr. Locklear or Professor Locklear, the son. If you didn't know that, that is Dr. Locklear's oldest son. That's why they look scarily identical. Well, 80 years apart, but similar. So, in any case, one of the things you talk about is true sources of randomness. It's actually very difficult to have a true random number generator. That's why they always throw, if you read about them in books, they say pseudo random number generator. We do the best we can to give you an even distribution of random numbers, but you know, if you're working on something that is highly dependent on random data, using the built-in random class is probably not appropriate. For everything we'll ever have to do, and probably for anything you'll ever do even after you come out of school, it's probably good enough. But if you're doing something real sciencey that really requires pure random information, my guess is the random class is probably not going to cut it. That's why they have all sorts of things, like they have an interesting research for source of randomness is they'll take like a computer lab and they'll install a program on all the computers, and what they actually do is they capture the information of how people use the mice, all those XY coordinates, and turn it into data that just fills into this file from all the different computers. So one might think that's fairly random, right? Totally not random. There's like a pattern to how people, because our operating systems dictate where we move the mouse. So you have obviously you're moving to the start button very often, so you're going to get that same streak of data fairly often, or at least within that swath, right? So really interesting. It's very difficult to find true sources of randomness, even in nature, which I think in Senior Seminar, that's where they start connecting it to creation and God, and there really isn't randomness anywhere. So very interesting thing for computer scientists to kind of consider, I guess. Okay, so we have our random numbers displaying. So now we can prove to ourselves that we have an array filled up with random numbers and it indeed is not sorted. I suppose we could probably roll the dice a whole bunch of times and maybe once in a blue moon we just happen to generate sorted data, right? But we can probably rely on the fact that this likely is not going to be sorted each time through. Okay, so now we need to sort it. So now this is where our ghetto solution comes in. So we're going back to something that looks like this. So let's see, let's say I have 81716, perfect. 81716. All right, so we have a collection of data that looks like that. Now, what I wanted you to do from this point is forget about Java for a second. Forget about computers for a second. Let's just write each of these numbers down on a Post-it note in front of us. All right, so I'm gonna just steal the center part so we look less programmy here. Okay, now here we'll move them out of line a little bit. That way they don't look so structured. There, Post-its. All right, now we have Post-its. So I've given you these 5 Post-its with numbers scribbled on them, and I've told you that, well, first of all, I ask you, are these numbers in order? And a human being glances at that and just says no. Well, how do you know? How do you know these are not in order, just from a human perspective? Remember back to last semester, we talked about one of the hardest things that human beings have to, the problem we have to solve to become good programmers is we have to figure out how to articulate how we solve problems. Every one of us can look at that and say, yeah, those numbers are not in order. But now when I ask you to tell me how did you know that, we have to slow down because it seems so trivial to us we don't even realize how we did it. Okay, so how did you determine, or how do you suspect you determined that those numbers are not in order? Go ahead.
We asked the account using questions in our mind.
Specifically, what questions? We asked a whole bunch of questions about this. What question might you have asked first?
What is the first number?
Okay, what is the first number here? 8, right? This guy. Okay, so now you have the 8. So I've looked at the first number. And what are we going to do with that number compared to the rest of the numbers? Okay, we haven't looked at them yet. So what would you plan on doing with this? So you've read in the 8. You've said, okay, well, I've looked at the front of it. That's 8. In order for this collection of Post-its to be in order, what must be true about that 8? Needs to be the smallest number. Okay, so I'm looking at this very first number, and in order for there to even be a chance that these Post-its are in order, this guy has to be the smallest number, or at least tied for the smallest number of all the numbers in this list, right? All right, so I'm going to look at the 8, then I'm going to go and look at the next number. So our eyes moved over to the next number. However we do that, right? Forget about that. I don't know if that's that important. We have equivalent structures in programming, right? How do I access bucket 1? How do I access bucket 2? So on and so forth. So we remembered that the first value was an 8. We glanced at this next guy. We saw that this number is smaller. So right off the bat, can we just conclude this list is not in order? Or the spread out Post-it notes is not ordered, right? We don't need to check any further because at the very least, the first 2 are out of order, so we can claim that it's not ordered. Therefore, if you would like it ordered, I have work to do. Okay? So let's start by writing just that piece. The ability to ask a question, is a list ordered? Make sense? We should get a whole lot of no's, a whole lot of falses from that function. And then we'll actually write a quick loop to see if we actually end up rolling the dice and seeing that it potentially is ordered. Okay, because we're going to have to evolve this solution. Right now, the only way we're telling if something is ordered is finding out if this is the smallest number, right? So I want to write a function that finds out if a particular number is the smallest number in an array. All right? So if this was a 1, if these 2 were swapped, that function might return a true. This number is the smallest number in all of these. It doesn't mean it's ordered, but it means that this guy is the smallest number, so at the very least, he's probably in the correct position. Make sense? So let's start writing. We're going to write a little function. And I use method and function interchangeably because they are synonyms for each other. So let's write a little function down here. Static Boolean is smallest. And let's have this guy take in a int val and an int array elephant. Let's switch it back to AR now just for our own sanity. All right, so is smallest is going to take in a value and an array, and this guy's going to return true if this value is the smallest value in that array and false otherwise. All right, so now, for example, I might call is smallest, passing in an 8 and passing it this entire collection. How do I determine if 8 is the smallest value in this entire collection? I need to look for values that are smaller than it. So I'm going to start with an 8. I'm going to go through every element of this list. I'm going to say, is this guy smaller than it? No. Is this guy smaller than it? Yes. As soon as I bump into one guy that's smaller than the value I was looking for, I can immediately return false. He's not the smallest. If I go through all the elements in here and don't find anybody that's smaller than him, I can then return true. The value you gave me does not have any competition in this list. Every single value in there is at least his size or bigger. Okay? So code for that is we're going to say our normal for loop for int I is equal to 0, I is less than ar.length, I plus plus. Now right here, ar.length. Length must be a what? Okay, definitely an integer. So in terms of object-oriented programming goes, is length a constructor, a method, or a field? And how do we know? Well, by looking at it right off the bat, is it an instance member or a class member? Okay, instance. Why is it an instance member? And that's going to be the answer to the second part of the question. Why is this guy an instance member of a class? Go ahead.
Because you don't need to call its full name, you call it AR.
I'm calling it with an instance of the class rather than the name of a class. So I'm calling this guy with AR. This isn't the name of a class. We can probably suspect that because it doesn't start with a capital letter. Therefore, this must be an instance member of that class. Class members come in 3 flavors: fields, constructors, and methods. Now, what kind of member is this guy? It's a field. Why is it a field? Okay, no parentheses, so we can rule out it being a method of any kind, right? So the other 2 guys, constructors and methods, both have parameter lists, open, close parentheses. All right, this guy doesn't have those, so he must be the 3rd dude. Okay, now, how would I know this is a constructor? If it were a constructor, how would I identify, how would I differentiate constructors from methods?
Doesn't a constructor have new in front of it?
So, big way is, if the new keyword's hanging around, I should strongly suspect constructors. Also, a constructor must have the identical name to the class that we're building. Okay, but the fact that we don't see the new keyword anywhere here, it's probably going to disqualify the remote possibility this is a constructor to begin with, whether this had parentheses on it or not. Then when we didn't see the parenthesis, we know this guy is a field. If this guy did have a parenthesis like it would for the string class, that means that that's an instance method. So for strings, the length of a string is an instance method. For arrays, the length of an array is an instance field. Okay? So being able to identify these animals in the wild. So just like bird watching. Okay? So, in any case, we're trying to find out if val is indeed the smallest value inside of AR. So we're going to create our go-to loop that will take I on a voyage through every element of AR. Each time through, we're going to ask a question. We're going to say if AR at bucket I is less than val, that is, if I find a value in there that's smaller than val, then I'm going to return false. Val was not the smallest value in there. How do I know? I found something that was smaller. That's what that question asks. Now, if I get through this minefield here in the end, and I didn't find any values that were smaller, and I'm done searching, when this for loop is over, I can go ahead and return true. He must be the smallest one in that list. Make sense?
Would it have to be less than or equal to?
What?
Well, what if the second one was a 1 as well?
Yeah, so is 1, if the second one was a 1, would it still be a true statement to say he's the smallest value in the list? Yeah, so we won't get inside this if statement. We'll still end up saying return true in the end. Yeah, because we're going to allow for ties. Ties are okay. All right, so now we have a little ability that will go through an array and take a value and say true, whether it'll return true if this guy represents the smallest value in that array. That is, there's no values in that array that are smaller than he is. There might be some that are equal, but none that are smaller than him. Okay? So if that's true, this whole function will return true. If there's at least one value in there that's smaller than he is, we'll return false and stop searching. Make sense? All right, so now we have that little tiny ability. We don't know how we're going to use it yet, but we do have that ability. Go back in here. All right, so right off the bat, I can say, all right, well, let's check out the 8. Is 8 the smallest value in here? Well, I compared it to itself. We're going to fail, that we're going to pass that test. Nothing, I'm not smaller than myself. Is 1 smaller than 8? Yes, it is. He's not the smallest value. Right off the bat, we're not in order. All right, but now let's say this was a 0. Not smaller than himself. This guy's not smaller. This guy's not smaller. This guy's not smaller. This guy's not smaller. So I get past the end of my for loop, and I just return true. He is the smallest guy in the list. Does that mean this list is ordered? No, it just means that this guy belongs in the front. That makes sense? He's the smallest guy in the list, therefore he belongs in the front. And then I need to go and look at more values. Okay. So we're going to assume that our list is not in order for this problem, our current solution to this problem, because it's highly likely in our situation that it will not be in order. And the worst case is it's in order and we're going to work very hard to keep it in order. That'll be the worst situation for us. Okay? So now if I were to ask you to put these guys in order, I had the post-it notes on the table. I say put these in order. Every one of us in here could do it, right? No problem. You're going to go through, you're going to find the 1s. Stick them out over here. Then you'll find the 6, put that there. Then you find the 7, put that there. Then you'll find the 8, put that there. Right? How did you do that? We need to ask ourselves, what are all the questions we asked to stumble upon that little algorithm? That's what we just did. We just performed an algorithm, right? Go ahead.
You check for the lowest value and then build a new array using it, building it up from the smallest.
Okay. So you went through here and you found the smallest value. Okay. So we're going to find the 1. So we'll write some sort of function that finds the smallest value. So right now you have a 1. And you're going to take that 1 and you're going to put it in a new array. Right? That's what you said? All right, so we'll find the smallest value, put it in an array. What do I do after I found the smallest value?
Remove it from the original one.
All right, so I need to get this guy out of that array? All right, what does it mean to get a guy out of the array? So this array currently has 5 elements in it, and I want to take this 1 out of there. Okay. Well, but do I just leave an empty bucket in there? Or is my new array a 4-bucket array? 4-bucket array. So this is one possible approach. So he wants to go through in this collection of 5 post-its. He wants to find the smallest one. And he's going to remove that value from that array, put it into another place, and then our collection of post-its is now one smaller than it used to be. Does that make sense? All right, so we need to find the position in this. So if we, let's start loosely connecting this to our programming. If this is position 0, position 1, position 2, position 3, position 4, we need to find the position in this collection of post-its where the smallest value lives. So in our first pass through here, the position will either be this guy or this guy, right? So position 1 or position 3. Depending on how you ask that question, you're going to determine that this is the smallest value or this is the smallest value. All right, so if I'm trying to determine, if I'm looking at those post-its and I'm trying to determine the position of the smallest value, how would I go about solving that little problem? So I have a function, for instance, static int pos of smallest and an integer array. And this guy should return the integer position, 0 through ar.length minus 1, of the smallest value in that array. Just the position. I'm not removing it. I'm not doing anything else other than identifying where it lives. So if I'm looking at this and I want to identify where the smallest guy lives, how would you go about that? As human beings, we can glance at that. We see we have a couple of 1s there. So the correct answer is either going to be a 1 or a 3. Correct? Smallest value lives at position 1, or the smallest value lives at position 3. Pick your poison. Okay? That's our human solution to this. Now we got to figure out how did we figure that out. We did that pretty quickly, but we would become less. We wouldn't be able to do that as quickly if we had a much, much larger set of numbers, right? If I put 1,000,000 numbers in front of you, we're all of a sudden at a point where we're not going to just be able to pick the smallest value out at a glance like we can here. So how did you determine that the 2 1s were the smallest value? Let's slow our mind down and try to ask ourselves, what questions did we actually ask? So here's our array, or in our real life example, our collection of post-its. And I'm telling you to tell me what position in this collection of post-its is the position of the smallest number. We have our answer. Now I need to know the how did you come up with that answer. What do you think?
Is there an index of kind of method for arrays?
Do you know about it? Nope. Go ahead.
You for loop through the array and call it as smallest of each I value.
Okay. So you're going to go through every element of this array. And we're going to have some winner up here, right? Or starting winner. So maybe we suppose that the very first guy in the array is our current winner. As far as we know, he might be the smallest. Okay? Now we're going to walk through this array and say, is this guy smaller than him? Well, that's kind of a waste of time, but we're going to do it anyways just to support the algorithm. So we're going to say no. Is this guy smaller than him? Yes. So let's go ahead and replace our current winner with that value and then keep going. Is this guy smaller than him? No. Is this guy smaller than him? No. Is this guy smaller than him? No. So we've now stored the value of the smallest. What I really want is the position of the smallest. So I could have said, let's set the position of the smallest at 0. Is the value at bucket 0 smaller than the value at, in this case, bucket 0? No, they're tied. Is the value at bucket 1 smaller than the value at bucket 0? Yes. So replace the position of my smallest with the new position of my smallest? Is the value at position I, which in this case is 2, smaller than the value at position 1, my current smallest? No, no, no. So once I'm done, I can return 1, which is the position in this array where the smallest value exists. Go ahead.
It's like a slightly different way of doing it, but like say that you have the 8, and every time that you're not smaller, you add 1 to that bucket's position. So you have 8, you realize that 1's smaller, you're going to add 1 to the position, like a temporary integer for it. You see 7, you add 1. You see 1, you add 1 because it's still smaller, and then 6, you add 1, so you know this position is going to be 4. And then just do that for each number.
All right, so you want to start off at 0?
Yeah, well, yeah, the value, like, I don't know, I was saying, like, kind of create a new variable.
So you start this guy off at 8 for the first thing, and then you want to have a second variable that keeps track of a count?
Its position.
Okay. So since that guy's not smaller, we'll leave it alone, right?
Yeah.
This guy is smaller, so you want to add 1 to this.
Yeah.
This guy is smaller, so we're going to add another 1 to this.
Mm-hmm.
This guy is smaller, so we're going to add another 1 to this. This guy is smaller, so we're going to add another 1 to this. But the fourth bucket is not our smallest.
I know, but I'm saying if you just did that for each number, though, and then you put them, like, you'd see the 1, and that'd be 0, 0, 0, 0, and then so you'd know that would be in the 0 bucket.
Oh.
Like, if you did that for each of the numbers, you could figure out.
I got you. So from a sorting perspective,
yeah.
You're not solving this problem. You're solving the whole sorting problem. You're saying what I can do is I can take a value and I can go through and doing this math thing, figure out where he should ultimately live, and then plop him there.
Yeah, and you can do that for the smallest one as well.
Yep. Yep. And that's a reasonable way you could have gone about sorting. Okay. But that's not part of the problem. That's not this problem.
Right.
Problem we're solving right here is just find the position of the smallest, looking for a little tool. So what he just described is a kind of a micro algorithm for sorting an array of elements, right? Let's find the position where this guy should ultimately live in the array and then run with it, okay? But it still requires us to be able to remove stuff from the list and that kind of stuff. So let's go with this guy where we keep track of the current winning position. We'll assume the current winning position is 0. Keep going through until we find the actual position of our smallest. All right, so that algorithm looks like this. Is bucket 0 smaller than bucket 0? So is bucket I, which is currently 0, smaller than bucket winner, which is currently 0? No. Is bucket I, which is currently 1, smaller than bucket 0, which is currently winner? Yes, so we'll change this to 1. Is bucket 2 smaller than bucket 1? No. Is bucket 3 smaller than bucket 1? No. Is bucket 4 smaller than bucket 1? No. We're out of things to check. The winner was whatever's at bucket 1. Okay, this is the position. And we're writing a function that returns the position of the smallest value in this array. So we'll say int pos is equal to 0. Have our for loop for int I is equal to 0. I is less than ar.length I++. If AR at bucket I is less than AR at bucket pos, then pos is equal to I. In the end, return pos. So this is the Java version of that algorithm. Assume that bucket 0 is our winner. Go through every single bucket in the array. Ask the question, is the current bucket we're looking at smaller than the value at our current winning position? If yes, update our current winning position. Do that for all the rest of them. When we finally exit out of this for loop, pos should hold the position of our smallest value. And we'll go ahead and return it. Make sense? All right, so let's go ahead and test this real quick. So we'll display our values here. And then we're going to go ahead and we're going to say driver dot, what would I call it, position, pos of smallest, passing it AR. And then let's print that out. Let's print see if that little widget, that little tool works. So here's my array. Bucket 0, bucket 1, bucket 2, bucket 3, bucket 4. We can see that bucket 2 is our smallest value, and that's what pos of smallest, or smallest pos, whatever we called it, returned to. Okay, so now I have a way of identifying the position of the smallest. So this guy identifies position of the smallest value. Okay, this guy determines if a val is the smallest in an array. Having a position, could I also then remove the value at that position from our array? What is that going to take? How do I remove a value from an array? So I've now determined that this guy is my smallest. The guy at position 1 is the smallest. So I'm going to need to take him and do something with him here in a minute. But when I take him out of this array, I need this array to literally shrink in size by 1. And now this is a weakness of arrays. Why? Arrays are fixed size. When I built him, he was built in a place in memory capable of holding exactly 5. So I can't just take a guy out and say, okay, now you're capable of holding 4. I need a new array. I need an array that's 1 smaller than the old array. Okay, so what does that mean? That means if I have this guy, and he's in an array of size 5, and I want to remove bucket 1 from that, very first thing I need to do is I need to create a brand new array. Actually, let's just copy 2 of them. That's 1 smaller than the original. It's a bunch of blank buckets. Okay, then I need to go through and I need to say, okay, well, I want to remove this guy. So you can think about that like I want to keep everything but index 1. I want to keep the 8. I want to keep the 7. I want to keep the 1. I want to keep the 6. So we're going to put the 8 in here. We're not going to take in that index because that's the one we're removing. I want to put the 7 in here. I want to put the 1 in here. I want to put the 6 in here. So a brand new array was just built that is a copy of the original array, but 1 bucket smaller because I have not copied over the guy I want to return. Make sense? All right. Then I've copied all the elements from the original array into the new array except for the guy I'm removing. Then I need to set my pointer for my old array. So remember, this is AR, so we're kind of squeezing our programming stuff back in. So let's just use AR and elephant for this example here. Maybe we call this guy temp. And temp's at position 200. I built a brand new array capable of holding, in this case, 4 integers. And he got a pointer to where that guy lives. And I filled it up with everything except the index I wasn't keeping. Okay? Now, I need to set AR, this guy, to point to the same place as this guy, abandoning the original array. But not until I've preserved this value. As soon as I disconnect this, as soon as I say AR is equal to temp, that is both AR and temp both point to the same place, that'll update AR's memory address to 200, I've lost the ability to say AR at bucket 1. So I'm going to need to preserve that first. I need to copy this value over into a temporary variable or something like that, int value to return, something like that. Then I can do this. Yep.
So because arrays are passed by an address, would you suggest then if say you had like a sort function, would you prefer to make that void instead of returning?
Absolutely. Yeah, otherwise it's redundant to do the same. It's redundant to return memory address 100 to overwrite memory address 100. So what he's asking is shouldn't, if a sort function for an array, shouldn't it return void? Yes, because we can do all the sorting at the same place in memory. We don't need to give you the new house. We fixed up the actual house. We changed it in place. All right, so now we got to do all these parts. So step 1 is, let's say 1, preserve value to return. 2, make new array 1 bucket smaller. Step 3, copy all elements from original array except the one we are removing into the new array. Step 4, make old array point to the new array. Step 5, return the removed value. Oh, I get it. I didn't have to rewrite the 4s and stuff. I thought it stopped doing it for me. That makes sense? That's our algorithm. That's our steps that we need to do. Okay? So we're going to write a function called remove at index. So we just found position, or remove at position, however you want to call it. So we called this guy position of smallest. Now let's say static int remove at index, and this guy will take in a int index and an integer array AR, the array we're removing it from. All right, and what does step 1 say to do? It says preserve the value we're going to return in some sort of variable. So int val to return is equal to AR at bucket index. I know I'm going to be destroying that guy or losing access to that guy shortly, so I need to preserve it. So I know at the very, 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 very end, notice here it says return the removed value. I know at the very end here, I'm going to be returning val to return. That's going to be my last step. In between, I need to do steps 2 through 4. Okay? Step 2, make a new array 1 bucket smaller. Well, how many buckets are in AR? How many buckets are in this guy? AR.length. So I would say int array, if we call this temp, is equal to a new int array of size AR.length minus 1. There's a brand new array that's 1 bucket smaller. Right? Okay. Well now, what's the next step? Copy all the elements from the original one except the guy that was already in there. The guy that we're removing, rather. Okay, copy everything except him over to the old one. All right, so how do we do that? Well, the most straightforward way of doing this, not necessarily the best way of doing this, would be copy everything up to but not including the original that we're returning. So maybe write a loop for int I is equal to 0. I is less than index. I plus plus. And then we'll say temp at bucket I is equal to AR at bucket I. So that'll partially fill up temp with everything up to but not including position index in AR, because that's the guy we want to get rid of. All right, so this is copy everything from AR before the guy we're getting rid of into temp. Then have another loop for int I is equal to 0. I'm sorry, for I is equal to index plus 1. Start at one position after the guy we're removing. Keep going as long as I is less than AR.length, I plus plus each time. Okay, so now we know that I is actually one bucket greater than its corresponding position will be in temp. So when I'm copying bucket 3 from AR, I'm actually copying it into position 2 of temp. Okay? So I'll be saying temp at position I minus 1 is equal to AR at position I. Because we've skipped over a value in I. Or in AR rather. Alright, so after these two loops, I've copied everything before the value we're returning, index, and everything after index, but not index itself, into temp. So now temp is filled up with all that stuff. Finally, make the old array point to the new array. So now that temp really has what we want our new array to look like, we'll say AR is equal to temp. It'll make AR point to the same place that temp points to. Finally, return val to return. All right, so now, most of us should be able to read this code. Most of us should say that we would have had trouble writing this code. Most of us, as human beings, should say this wasn't horribly easy because we had to remember how we solve problems, but every one of us in here should be able to write this after thinking about the problem for some amount of time. So the time we spent for this guy was spent getting this recipe, this series of steps that we had to follow. Then we just converted that recipe into the equivalent Java code. Okay? So let's test this now. So right now we are displaying our array. And here, I'm just going to do something here to make our display look a little cleaner. That'll separate it from our values. I just put some asterisks on either side. So we'll generate our array, fill it with random numbers. We'll find out the position of that guy. But I'm going to use that position now for something else. So the position I'm going to use, let's just say int pos is equal to whatever that guy returns. Then let's say driver dot remove at index. Index pos from our array AR. And internally here, remove at index actually changed what AR points to. Changed that pointer. So even though this guy returned an integer that right now I'm not using, our original array has been rebuilt and now points to a new place, and we should be able to see that. So after I remove an index, I should be able to call this exact same line again, seeing my brand new array with, in this particular case, the smallest value taken out. All right, so let's go ahead and run this. So here's my original, 17600. Oh, ruh-roh. I gotta see where I went wrong on my code here. Display AR, get the pos of AR. Let's print that out real quick. So it should be position 1. 0, 1, that is the smallest, so I want to remove position 1. Then we're removing an index, passing it pause and passing it AR. Remove an index. Here, we're going to preserve the value that we're going to return. Let's just make sure that we got the right value. So this should return in this case. Smallest value is a 0, so we printed out a 0 that lives at position 4. All right, so it is removing the correct value, but it's not actually removing. Let's see what line I left off. So in that last case, we were removing position 4 from AR here. That's the value we're returning. That was the correct thing. Here's a brand new array, temp. Spin through AR, copying each element into temp. Spin through AR again, copying each element into temp. Then we set AR equal to temp. No, because this should be, that should be a pointer to the value, AR.
Is that changing the entire class's AR or the print thing?
Both. Both. So if I print out AR here, let's just do a system.out.println AR. That's going to print out one memory address. And then if I come in here and I say remove an index and I print out AR here, it should print out the identical memory address. So I should see two memory addresses amongst all this other crap printed out, and they both should be the same memory address. CBF7, CBF7. So both of these guys are pointing to the exact same place. Then let's print out the memory address of temp. So let's get rid of those memory addresses for AR. So here's the memory address of, well, actually we'll print out the memory address of AR, then we'll print out the memory address of temp here. Then we'll print out the memory address of AR a second time, right after this. So we should come in here. We already saw that AR here is the same as the AR above because this guy is passed by address. Then we're going to print out the new memory address that is temp. Then we're going to fill up temp with stuff. And then we'll print out AR after we set it equal to whatever temp is equal to. Original AR, original temp, new AR. Then we're returning the value to return. If I print out AR again up here, that should show the new value. Oh. That is weird. That's not how it's supposed to work.
Aren't you in the method where you're changing the value for AR, you are passing an array and you're naming the array that you're passing it AR, and you're changing the method, or you're changing the memory address of that specific methods, but not the entire classes, where up above you're calling the entire class, not that specific method. That's what's looking like.
Well, I mean, we've already proven that they are the same AR. But what the output here is showing that this is original AR, this is original temp, this is new AR after we set it equal to temp. But this is AR back in our original program, which then says that because this guy is in a static context, passing an array here is passing it, well, it's not passing it by value though.
Isn't that why you would need to do this.ar to change the memory address of the array so that will bring up the new
Well, this.ar doesn't exist because we're in a static context. So I can't say this.ar because we're not in an instance of this. Yeah, this is the way it's supposed to work, and this is the way it always has worked. So, well, at least I think I've always done the example this way. See, let me try to do something here and show you the difference. We might have just stumbled on something I've never actually done before in Java. Let me just create a new class file here real quick. It's not going to really change our logic here. We just have to do it inside of an object. Let's just call this guy sorter. Okay, we'll throw all this crap in here. We'll get rid of what I need to do. Take all the statics off. Just re-indent here. Okay, and then what we're going to do is we are going to, well, it should actually be good enough. Go back to driver. We have our, I'm not going to use the guys down below. So we have our new array. We filled it up with crap. Great. So now we're going to go ahead and we're going to create a sorter s is equal to a new sorter. So an instance of our little object. We'll say s.display, AR. Then we'll say s.pos of smallest AR. Then we'll print out pos. Then we'll say s.remove at index AR. And then we'll say, that's our memory address stuff. And then we'll say s.display AR. Why is that? I might have to amend my answer to your question. Just try something here. Static, void, change val, int array, AR. And then let's say AR at bucket 0 is equal to -2. So we'll do driver.display, and we're going to display AR. Then we'll say driver.changeVal, passing it AR, which should change bucket 0 to -2. Then driver.display AR, which should now show the thing with a -2 at the beginning. All right, so that changed it in line. So we see the change, right? We built AR, filled it up with crap, displayed AR, so here's the original version of AR. We passed AR into change val. It made a change to it here. And then when we came back out here, that change was permanent. We show the -2. That's the way it should work. But if I were to come in here and I were to create an integer array temp is equal to AR is equal to a new integer array of size AR.length, and then for int I is equal to 0, I is less than, actually let's just do this, I is equal to 1, I is less than temp.length, I plus plus, temp at bucket I is equal to AR at bucket I, so copy everything over. Then set temp at bucket 0 equal to -2, and then set AR equal to temp. All right, so this should effectively do exactly what we just did before, creating a brand new integer array, filling it up with, well, of the exact same size as AR, filling bucket 1 through the end up with the exact same contents as that are in AR, then overwriting bucket 0 with a -2, which should be different than what bucket 0 used to be because I'm only filling it with positive numbers, and then changing the value of AR, which is this AR, which should be the same memory address as the other AR that I'm displaying it. So it's back. But if I display it inside of here, I'll have the -2. This is going to bug the hell out of me. Java arrays pass by reference. That's old. All right, so it's, I didn't see anything there. So it's obvious that it is being passed by reference because we were able to directly change AR. I could say AR at bucket 0 is equal to -4. Let's do that. So I'm changing AR at bucket 0 to -4. I'm creating a new array with everything that was in the original one, copying everything over, changing bucket 0 to -2 here, printing out AR, which should show the -2, not the -4. But back here, when I print it out, it should show the -4. So this proves that it was passed by reference because I made the change right here, and that change had a global impact. This proves that I did change the value of AR to point to the same place as temp locally because it'll show a -2 there because I set it right there. But when we come, yeah, so there's a 3, there's a -2, and now we're back to -4. So there's evidence that it was passed by reference. There's evidence that we were able to set AR to be equal to temp internally. So the punchline of that should be that Java passes arrays by reference. We've proven that, but protects the global address of the array from permanently changing. Because that's what it did. If I say system.out.println AR here, it'll be back to its original memory address. Original memory address, and then inside of here, after I set it equal to temp, I'll change it to its new memory address. So we'll see original, new, back to original. Original, new back to original, 84B. Very interesting. And that is not how Java worked before this year. So something with the virtual machine is protecting that address from permanently changing.
Well, right now you are using Java 6 on your Eclipse.
Okay. Oh, yeah, you're right.
I don't know.
Well, I'm using the Java 6 runtime.
I don't know if it actually would change.
Yeah, that's interesting. Okay, well, so we'll come back next time. We'll finish. I mean, this isn't going to change our logic here, but it does change a little bit how Java works when it comes to passing by reference and passing by address. It does protect that memory thing. So we'll just go ahead and have it return the new memory address of our array. We'll store it in AR permanently, and then we'll get our change. So here, I'll just write that at the end of the video here. So we'll. I'll do it next time, just so we can talk through it.